In the last part, we were able to build a device in the lab that can switch the spin of the electron from maximum value to minimum value. Today, we will make this quantum computer carry out processes like receiving data as an input and then processing the data in a certain way and creating an output. The idea now is to build a device in the lab that allows us to switch the maximum spin of the electron to the minimum spin and vice versa. We all saw in the second stage of the experiment the magnetic field can affect the energy of the electron. Also, we found that the Schrodinger equation can represent the change of the electron energy when we advance in time. Now, we need to correlate these two concepts with each other to come up with a device that can use the Schrodinger equation to manipulate the energy of the electron, thus switching the spin from maximum value to minimum value. The Schrodinger equation in quantum mechanics tells us about the change of energy for an electron as we advance in time. This little example for an electron with three different discrete energy levels, low, medium, and high, can be written here as a superposition of all three quantum states. Also, every quantum state, it has a coefficient linked to it. It's called the energy operator, e to the power I e t over h bar. And the maximum spin for an electron along the x-axis is a quantum superposition for the same electron having a maximum and minimum spin along the z-axis this time. Also, in this Schrodinger equation, we have operators as coefficient. We call them the energy operators, e to the power minus I omega t. And we said in the lab we can manipulate omega by manipulating the energy or the strength of the magnetic field along the z-axis as we did in this device. So we can change this formula now from plus or from summation to subtraction, thus changing the maximum spin for the electron along the x-axis to a minimum spin for the electron. Here is the minimum spin along the x-axis. It can be written as a superposition along the z-axis but with a minus sign. So we change the maximum spin for an electron along the x-axis to the minimum spin along the x-axis simply by manipulating the energy of the magnetic field along the z-axis. If we call the maximum spin along the x-axis qubit 1 and we call the minimum spin along the x-axis qubit 0, this is how we change from 0 to 1 and 1 to 0 in quantum computers using magnetic fields and Schrodinger equation. The classical computers rely on certain algorithms to carry out processes. They have what we call logic gates. A logic gate can perform a simple calculation or simple calculus, but with a whole bunch of them built into the computer can perform very complicated calculations. The qubit is an electron having one of two positions, up or down. It can be in the up position if the electron has a maximum spin along certain axes. It can also be in down position if it has minimum spin along that axis. It can also be in a quantum mechanical superposition of both up and down at the same time. Let's try to simulate a very tiny quantum mechanical system consisting of only 20 electrons using a classical computer, just to figure out how many classical bits are required to simulate such a tiny quantum mechanical system. As we know, the electron can be in up or down position, but also in quantum mechanical superposition, up and down at the same time. So the total number of classical bits required to simulate such a tiny quantum mechanical system is 2 to the power of 4, which is an enormous number. So we can say with complete certainty that we cannot simulate quantum mechanical systems using classical computers. But the opposite statement is true. We can easily simulate classical systems using quantum mechanical computers, even if the classical systems has a large number of degrees of freedom. And that's because we're here and there is a universe. Everything in this universe is made up of small particles governed by the rules of quantum mechanics. So the quantum mechanical systems have been very successful so far, simulating classical systems like us and the universe. Let's go back to the algorithms of quantum computing. There are three stages: input, process, and output. In quantum computers, input and output are both wave functions, which means they're superpositions of things we can measure. The process stage is a Schrodinger equation that can evolve in time with a certain E operator. This E operator we can dial, we can fine-tune using a certain device in the lab. As a first rule, the input and the output are both wave functions, superposition of possible states, so we cannot get definite value for the outcome or the input. Because superpositions are involved, we will get quantum interference. Quantum interference happens when parts of the superposition interfere with each other. As they interfere with each other, we will get probabilistic outcome. That means we'll never get a definite outcome. Which makes finding a definite outcome out of the probabilistic outcome we got because of the interference is the most important thing in quantum computing. To clarify, let's build a small quantum computer that can do little calculations. Remember the algorithm: input, process, and output. Input and output are both wave functions, and the process is the way we advance with the Schrodinger equation, and we evolve in time according to a certain energy operator. In the first example, we'll build a quantum computer that can carry out a simple process. It can take a quantum state 0 and turn it to 1, and take a quantum state 1 and turn it to 0. This is called the NOT gate. So simply, we'll build a quantum computer that can carry out the NOT gate. Let's represent the quantum state 0 by an electron having a minimum spin along the z-axis, and we give it a small matrix 0, 1. That means the electron is in down position. In a similar fashion, we give the electron a spin along the z-axis in a maximum value, and we give it this matrix 1, 0. So the question now, how we can apply the NOT gate, how we can change from 0 to 1 and 1 to 0. Remember, we can write this 0 and 1 according to Schrodinger equation as a superposition of two spins, maximum and minimum, but along the x direction this time. Also, we have the energy operator. We can adjust the omega, we adjust t in the lab to change this formula. So now, the energy operator that we require to transfer from 0 to 1 or 1 to 0, which means we apply the NOT gate, will be like this: minus I e to the power of I pi over 2. And then this matrix means we transfer from 0, 1 to 1, 0. So that means we should find a way to make omega t is equal to pi over 2. And this is easy to do now thanks to the device we had in the lab. We could manipulate the magnetic field in any direction to change the spin of the electron in any direction we want. Remember the relation between the energy of the electron and the strength of the magnetic field. E is equal to S vector B vector. S vector is the momentum of spin for the electron along the x-axis, and B vector is the strength of the magnetic field along the x-axis, which is something we can dial, we can tune by this device. Also, omega, the frequency of the electron inside, is equal to C, a constant, Bx, the strength of the magnetic field along the x-axis over 2. So we can get any value of omega we want by dialing this value, the strength of the magnetic field along the x-axis, using this device. Also, we can let the system evolve for a certain amount of time t. So we can control t, we can control omega. That's how we get pi over 2 here, and change this quantum state from 0 to 1. Also, the same way from 1 to 0. This way, we applied the NOT gate in this quantum computer. Through this algorithm, which was input 0 state, output 1 state, and the process. The process was an energy operator we built and we applied in the Schrodinger equation and let it evolve for a certain amount of time. So we transferred 0 to 1 and 1 to 0. So it's a Schrodinger equation manipulation using magnetic field in the lab. Let's do another example. We take a quantum state 0 and create a quantum superposition out of it. Also, we take a quantum state 1 and we create another quantum superposition out of it, but with a minus sign this time. The idea now is to adjust the values of omega and t to match the value that we require in the energy operator to transfer us from the quantum state 1 to the superposition with a minus sign. In this case, omega and t can be adjusted easily. T, we can just run the experiment for a certain amount of time. Omega, in this case, we have to change the magnetic field or the strength of the magnetic field along the y direction. In this way, we get the certain value in the energy operator that transfers us from 1 to the superposition of 1. Finally, let's build a quantum computer that can apply the controlled NOT. The controlled NOT means if we have 2 qubits, if the first qubit is 0, we do nothing. If the first qubit is 1, we change the second qubit. So for this example, we have quantum state 0, 1. The first qubit is 0, so we do nothing. The output will be similar as the input, 0, 1. But if the input is 1, 1, that means the first qubit is 1, so we change the second qubit. The output will be 1, 0. And in case the input is 1, 0, the first qubit is 1, so we change the second qubit and we apply the NOT gate. So it becomes 1, 1. The algorithm should not be that different, except we'll have an extra stage. Because we have 2 qubits as an input, we take the first qubit and then we see if it's 0, we do nothing. We give the same output. If it's 1, then we go to stage 2 and we ask stage 2 to process the second qubit. That means applying the NOT command on the second qubit and giving a new output. This is the idea of quantum computers: input, process, and output. In the process stage, we also do the most important work. We manipulate the strength of the magnetic field and we run the experiment for a certain amount of time until we get the specific, the right energy operator in which we can use in the Schrodinger equation to transfer a state or quantum state from certain position to another position.